So how the GUI works is I send commands to my GUI class running on Python from this Xbox controller, and this will send it to the other computers, either the BeagleBone or an actual computer, through the internet. And that computer will then intercept the command and then send it through serial to the Arduinos. And then the command will then bounce back confirmation saying it has received such a command. And then this will pop up on my GUI. So what happens is I send the command, my command line console, my makeshift console, output saying, oh, my controller has been set to such and such. And so that shows up on controller input. The other computer on the other end will send back information, and then I will receive updates on the values of the motors that it has recorded.
Yeah!
One thing that was really useful about this GUI is the inclusion of sensitivity sliders. What happens is when I'm moving an arm, say I need a certain voltage, and so I set the sensitivity slider from something from 0 to 1000 so that the maximum value I can get from going up as much as I can on an analog button is that maximum set. So this way I can allow for fine control. If I want something that's small, I set the sensitivity to really low, and so then I have really fine control.
Video streaming system consists of a HTTP server where we broadcast from a USB webcam, which we have mounted on the arm over here. And from this broadcast, we sample about 15 frames per second right now, and then the video streaming server converts that into a format called motion JPEG, which is basically a sequence of JPEG images compressed into a stream, and we can open that stream up on any other computer via the internet. And that is our video streaming system.
As you can see, it's already been fully assembled. We're working out the bugs right now. One thing to note about this, I think, that is we use right-angle gearboxes for all the vertical actuators, so that way we don't have to keep supplying power to the motors in order to hold it in a certain position. We chose this design just because it makes control a lot simpler, and it increases the lifetime of the actuators that we use. As of now, it's pretty much done, except down here we need to add the shovel grips because these prongs as they are not good enough to grab rocks with, and we need to tighten we have a timing belt and pulley system that currently controls the heading of the arm, and that's currently loose right now, so we just need to drill some belt tensioners on there. But once we do that, pretty much this thing is fully developed, and we can pick up things with it and move around, so it's pretty exciting.
Progress for the drivetrain isn't as far as the actuator and telecommunication. We are about halfway done with the development of our drivetrain module. We were, however, able to assemble the housing for the two actuators and get communication established between the controller and the motors. We are currently machining a belt tensioner for the timing belt and finishing machining for the rest of the swerve module parts. Currently, we have made good progress, but we still have much to do. We will be spending more time over the next 2 months in the machine shop and in the computer labs debugging the rover. We strongly believe that our rover will be finished and a strong competitor for the 2014 Robo-Ops competition. Representing California and the West Coast, we are the CAL-Rover team. Go Bears!